Yeah, so it's my pleasure to introduce Liu Jie from Chinese Academy of Sciences. So today he will talk about strictly her nav subsheaves in her tangent bundle. Please.
Yeah, thanks for the invitation. It's my great pleasure to have an opportunity to talk here, to have such a nice opportunity to present our recent work joint with Wenhao O from AMSS and also Xiaokui Yang from Tsinghua University. And I'm so sorry for the technical problem in the beginning. So let me start my talk. So today I'm going to talk about the so-called I'm going to talk about strengthening knife subsheaves in tangent bundle. The main motivation of my talk is to study the projective manifolds with the so-called positive tangent bundle. So let me just recall the very basic definition of positivity of vector bundles. So I will always work over the complex numbers, okay? So all the variety are defined over the complex number. So let me take a vector bundle E over a projective manifold X, okay? Over a projective manifold. So it's called ample or life. I will mean that if the tautological bundle O of P of E1 over the projectivization of E, PE is an ample line bundle or a life line bundle, okay? So here PE is just the projectivization of projectivization of E in the sense of quaternion. Okay. So basically, my question is, I want to study the following question. Okay. I want to say if you have a X is a projective manifold, okay, and such that you can find some subsheaf F in the tangent bundle of X, okay, is a positive. Maybe locally free subsheaf. Okay, then what can we say about the geometry of X? Okay, so let me start with the first result, okay, by the very famous result of Murray, okay. So if you consider X a projective manifold, then the tangent bundle, okay, X is ample. If and only if X is isomorphic to a projective space, Pn, okay. This is the first result. So in this case, if the subsheaf F is equal to the tangent bundle and F is also ample, this gives you a complete answer to the question above. So in the next case, we may consider the case tangent bundle is knife. In this case, we have the following conjecture due to Kampala and Pedernel, okay? Conjecture of Kampala and beta now. Okay, so you consider X to be a smooth Fallon manifold. This means the minus kx is ample. Okay. In this case, it is conjecture that Tx is life if and only if Tx is globally generated. Okay. So the next one, the later one is equivalent to say that X is isomorphic to a rational homogeneous space. Okay. A rational homogeneous space. So this conjecture is still largely open. In the general case, it is only proved in lower dimension. So I guess it's learned for dimension x at most 5. Yeah. So in my case, I will consider notion which is a positivity of notion of vector bundle between lifeless and ampless. That means it's weaker than the ampless, but it's stronger than the lifeless, which is called the so-called strictly lifeless. Let me start with the definition. So you consider line bundle over X, okay? A line bundle over a projective manifold over a projective manifold X. So this one is called strictly knife. If the intersecting number of L with any curve in X is positive, okay? For any curve in X, okay? And a vector bundle, okay, is strictly knife if it's a tautological bundle, OP of E of 1 over X, over PE is strictly knife. Also, we have another notion which is related to the lifeless, okay, which is called numerically flat. So this one is also important in my talk, okay? A vector bundle is numerically flat. We have a different definition. The first one is if and only if E is a knife, and the first chain class of E is trivial. Okay, and the second one is say that E is life, and also its dual bundle. E star is also life. Okay, this is a dual bundle. In fact, a strictly knife is very strange notion because we can compare it with the ample vector bundle. You can say that it's very easy to say that a vector bundle, an ample line bundle, an ample vector bundle, sorry, is never numerically flat, since its determinant, okay? Its determinant is always ample. That means its first chain class is always positive, okay? So it cannot be trivial, because in the definition, the numerical flatness means the knife and with vanishing first chain class. But for ample line bundle, the first chain class is always positive. So ample vector bundle cannot be numerically flat, but for strictly knife vector bundle, this is possible. A strictly knife vector bundle can be numerically flat. Okay, this is very huge difference between strictly knife vector bundle and ample line bundle. In fact, a strictly knife vector bundle can even be Hermitian flat, which means the curvature of this vector bundle is totally trivial. Okay, Hermitian flat, sorry. That means in the sense of differential geometry, this vector bundle is flat. Okay, it's totally flat, and we know that the Hermitian flat is stronger than the numerical flat. So let me start with an example, okay, which is very important in my talk. This example is due 2 months old. Sorry. So you consider C, let's say, be a smooth projective curve of genus at least 2, okay? And in this case, then you can find a vector bundle E over C, okay? Such that, satisfying the following property. The first one means E and E star are numerically flat. Okay, that means the first chain class of E and also E star is trivial. Okay, and again, E and E star are both strictly knife. So this should be a bigger problem for us to study the strictly knife vector bundle, because in some sense it can be numerically flat, and there are many criteria we cannot use. For example, it's the strictly knifeless is not closed under YG product or symmetrical product or tensor product. Okay. Any question? Okay. If there's no question, let me start our second example. So if you consider a vector bundle over the projective line P1, okay. So by the theory of Grothendieck, okay, you can write E as a direct sum of line bundles over P1, okay, direct sum. Direct sum of line bundles over P1, and E, this guy is strictly knife. So you can say that this just means all the AIs are positive. Okay, this means in fact E is ample. So over the projective line, strictly knife means strictly knifeless just means ampleless. Okay, so this is very nice. So now the question is, so X to be a projective manifold, and if you consider F to be a subsheaf of the tangent bound of X, so it's a strictly knife, locally free subsheaf. What can we say about the geometry of X? Okay, so this is a question. The first case, of course, we want to study the case where F is equal to Tx. Okay, so you just consider the case F is equal to Tx. Okay, we can compare it with the theory of Murray. Okay, so we look at this theory. Because in Murray's theory, we prove that the tangent boundary is ample if and only if X is a projective space. And for the conjecture of compound and Peter-Nel, it is conjectured that final manifold with the knife tangent boundary. So then the tangent boundary is globally generated and X is the rational homogeneous space. So we may conjecture that Tx is strictly knife is something between knifeless and ampleless. So it's something similar. In fact, it is proved by Dorley, Wenhao O, and Xiaokui Yang that for the tangent model, this is things is very nice. I mean, X should be, we consider X a projective manifold. And if the Tx is strictly knife, then X is the projective space. Okay, so this just means that Tx is ample. So this means that for projective manifold, a tangent boundary is strictly knife if and only if it's ample. So this is very special because we have seen from the example of Mumford. Okay, this example we say that this is not true for general vector bundle. Okay, so now the question is we want to study the case F is a Rayleigh subsheaf of Tx and F is not equal to Tx. Okay, for the case F to be ample. Okay, this is studied before by many mathematicians, and the result is as below. So it is proved by Andreada and Wisniewski. So you consider X to be a projective manifold, and such that you can find the subsheaf F in the tangent bundle, which is ample, locally free, then they can prove that X is in fact isomorphic to a projective space, and we have two possibilities for the sheaf F. Either F is equal to the tangent bundle, okay, or F is just a direct sum of OP1. Okay. So, for example, for the result of Murray, it can be generalized to the to a strictly knifeless. We must if we can generalize this result to a strictly knife subsheaves. The question is the problem is maybe the first answer is negative because if we back to the example of Mumford, okay. in Mumford example, we consider C to be a curve, okay, of genus at least 2. You consider E to be vector bundle of rank 2 over E over C, okay. You consider PE over C, okay. This is S. Now you consider relative tangent bundle of S over C, okay. This guy is a subbundle of T of S, and you can say that this guy is isomorphic to OP of E2, okay. We have seen that this bundle is strict enough, okay. So the relative tangent bundle of S over C is also strict enough, okay. That means that you can find a projective bundle such that the relative tangent bundle is strict enough, okay. So that means if you have a projective manifold such that the tangent bundle contains a strict enough subsheaf, it's not necessary to be the projective space itself. So there are other possibilities. So in my talk, in my joint work with Wenhao O and Xiaokui Yang, we show that the projective bundle should be the only exceptional possibilities. That means you take X to be a projective manifold such that the tangent bundle of X contains a strict enough, locally free subsheaf F. Then we have two possibilities for X. The first one is X is isomorphic to the projective space Pn, okay? And F is ample in this case, okay? And the second one is you can find X amorphism from X to a projective manifold T, okay? Which is a projective bundle, PD bundle. And T is a hyperbolic manifold of general type. Yeah, if you consider the example of Mumford here, okay, C is of genus, okay, the genus of C is at least 2. So of course C is of general type, and C is also hyperbolic, okay. This is well, okay, sorry. Let me just recall the definition of hyperbolicity. So recall that T is hyperbolic. That just means for any holomorphic map from C to T is constant holomorphic map. Okay. So for curve, okay, hyperbolic curve just means the genus of the curve is at least 2. Okay, this is well known. Okay, as a corollary, we get a new characterization of the projective space. Okay, if you take X to be a projective space, to be a projective manifold, and such that you can find a locally free strict enough, subsheaf in the tangent bundle. Okay, and if the fundamental group of X is virtually solvable, okay? Then X is isomorphic to a projective space. So for example, in the example of manifold, you cannot change C to be the projective line P1, because we have said that for P1, ampleness just means for P1, okay? The strict knife vector bundle is also ample, and also it cannot be changed to be an elliptic curve, because for an elliptic curve, its fundamental group is abelian, so it's of course it's virtually solvable. So in this case, you cannot construct such an example, okay, over C. Any questions? Okay, so let me start with a general construction of examples satisfying our theory, okay? So we start with some general construction of example. General construction of examples. So we consider T a projective manifold, okay? And we assume that you can always construct a vector bundle E over T, okay? A vector bundle such that E is numerically flat, and also it's strict enough. For example, for T equals to a curve C of genus at least 2, and a rank of E equals to 2, okay? This is an example of manifold, okay? In general, in general, if we consider T to be a curve of genus at least 2, and for any R positive, okay, maybe at least 2, you can construct such an example, okay? As above. This is done by Sabrama, okay? So we do have such an example over the curve of genus as least 2, and for higher dimensional in our work we have constructed such an example over a surface, okay? In general dimension, the construction is much more complicated. I don't know a general construction of such a pair E and T, okay? But I guess the construction is possible, but the structure of T is the geometry of T should be very, very special, okay? Anyway, just to assume that we have such a pair, okay? E and T. So first, the first example I want to construct is a sub-bundle in the tangent bundle of Tx, okay? As a sub-bundle. Okay, so you consider just X to be the projectivization of P of E, okay, over T. And you consider the relative tangent bundle, okay, T of X, T over, this is the sub bundle of Tx, okay. I want to claim that this relative tangent bundle is strictly enough. So it's not difficult to prove this, because if you consider the relative Euler sequence of x over t, okay, you consider this is pi projection pi star of E star tensor with O of PE1, okay, and you have a surjection to the relative tangent bundle, okay, because E is a knife, so this guy is also life. So because it's a product of a life vector bundle is always life, and we have seen that this guy is strictly life by our assumption, okay. So if you take the tensor, this just means that the tensor is also strictly life, okay. And you take a quotient of a strictly life vector bundle is also strictly life. Okay, so here we say that because strictly lifeless is preserved by quotient. Okay, this is our first example where F is a sub-bundle of the projective bundle. Okay, in the next example, I want to construct an example where F is not a sub-bundle, but is a subsheaf. Okay, you take F in the tangent bundle of X. Okay, is a subsheaf, not sub-bundle. Okay, we start with another vector bundle F over T. Okay, another, for example, another strictly knife or ample vector bundle. Vector bundle. And you set Q to be the direct sum of E and F, okay? Because E is a strictly knife, okay? Strictly knife, and F is also strictly knife. So this just means the vector bundle Q is also strictly knife. Okay. Now you consider X, you let X to be the projectivization of Q. So this is a projective bundle over T. Okay. You again consider the relative Euler sequence of X over T. Okay. X and pi star, Q star, tensor with O of P of Q1 to the relative tangent bundle of X over T, okay? And you have a sub bundle here, you just put back of the vector bundle E star, okay? Because E is a direct summand of Q, so E star is also a sub bundle of Q. So you take a put back, this guy is a sub bundle of pi star Q star, so you can tensor it with O of P Q1, okay? We let this shift to be F, okay? If you look at this one, because E is numerically flat, this guy is in fact life, and this guy is strictly life. So this just means F is strictly life. So you consider the composition of this map, sigma. You can say that sigma is an injective morphism of sheaves. Now, this is, in fact, this is done by the work of, for example, by the work of Nohe, by AGEA, Duzai, in their paper, published in Inventions in 2018. Okay, and we'll also need a result of Horvin and Peter Nell. Okay. Yeah. Then, in fact, you can use a survey of AGEA, sorry. AGEA Duzai. For such a foliation above, okay, we have a less description of its leaves. This is published in 2013. Okay. In fact, you can find a finite a top cover effect at top cover of X. Okay. Maybe I take it to be mu also, and you can also find a almost holomorphic map from X delta to a projective manifold T. Okay. Almost holomorphic, okay, such that general fiber is Albanian variety. General fiber we denoted by F, and you look at the product of F over the sheaf F over the fiber F. This in fact is a direct sum of the trivial vector bundle. Of course, this one is not strict enough. Okay. So this just means F itself is not strict enough. Okay. This is a contraction, contradiction. Okay. So a contradiction. Okay. So that means, so in the first step, we have proved that if the tangent amount of X contains a strict enough subsheaf, then X is unirooted. And then it's a very standard method in algebraic geometry to use rational curve to create a projective bundle over a large subspace of X. The second step, this is already done in the work of Arroyo. Okay, you can find an open subset of X. Okay, open subset of X, and the key point is that you can take this X0 to be very large, such that its codimension is of its complement is at least 2. Okay, and in this open subset, it's a projective bundle. Okay. Maybe a PD bundle. Okay, in my talk. Now, our main theory is to try to show that our goal is to show, okay, we denote this map by phi 0, okay, to phi 0 can be extended to the whole X. Okay. Now, if we want to do this, we just consider the Chow variety of X, okay? The image of, you take the image, okay? You take, here, I just write down the following diagram. Sorry. So you take the T, let T be the closure of T0 in Chow variety of X, okay? So you have such a diagram, okay? And it's T, okay? And you take the universal family here, okay? U here, okay? Universal family. Okay, those two guys may be singular, so we may resolve the singularity T prime and also X prime here, okay? And even we can do something better, okay? You can take a resolution as you like, any resolution as you like, and it's a general factor about this family F prime to T prime. This is a projective bundle. Okay, this is a projective bundle. Okay, so basically, if we consider this guy, we have the following diagram here. Okay, and this is subset of X, and you take X prime here, and you take T prime here, and this is subset of T prime. This is subset of X prime also, and you can take this guy to be a projective bundle. Okay, so right now, any question? Okay, if there's no question, let me start. Let me continue. Okay, so right now the fourth step, we try to understand what happens for this guy. Okay, you take F here, you take F star. You consider F star of F. Okay, in fact, over X prime. Over X prime, okay? You consider this one, this sheaf over X prime. The first factor we can prove is that, in fact, this one is also contained in this tangent bundle of X prime, okay? So right now, we want to study this pair, okay? We want to study the pair, okay? F star, F, and X prime over T prime. Recall that this is a projective bundle, okay? We want to understand the geometry of this pair. In fact, we have a very nice description of this pair. Let me just study the theory for the projectivized bundle, okay? Population, okay? If you take X equals to P of E over a projective manifold T, okay? And you take a subsheaf F in the tangent bundle of X such that the restriction of F over a fiber of F is strict enough. So here, F is a fiber of T of E to T, okay? So this is just an arbitrary fiber of this projective bundle, and we assume that F is strict enough over this fiber, and also F itself is enough, okay? This is the assumption. Okay, we have a very nice description of such a pairs. The first case is then one of the following holds. The first case is F relative tangent bundle. Okay, and this PE over T is a flat vector bundle. Sorry, is a flat projective bundle. Okay, that means you can find a representation of P of T, pi 1 of T to the PGL of CR maybe, such that PE is biholomorphic to the Cauchy projective bundle, okay, which is just a T times CR Cauchy by pi 1 of T, okay. So from here you can see the relation, in fact, the relation of the structured knifeless subsheaves in the tangent bundle and also the fundamental group of the total space. Okay, you can compare this this result with our first example here. Our first example. So a sub bundle here. Okay, this is in fact in our case here. Okay, so this is exactly the first example constructed here. And now I want to say the second possibility for F. Okay, the second possibility is that F itself is so-called numerically flat, numerically projective flat. Okay, this means if you consider the Q shift, okay, F tensor with the Q class 1 minus 1 over the rank of F times the first chain class of F. Okay, this guy is knife. Okay, because you look at the first chain class of this guy is equal to 0. The former first chain class of this guy is 0. So this is knife. This just means in some sense this Q shift is numerically flat. Okay, that just means that if you normalize, okay, to make the first chain class of F to be 0, then this F is flat, numerically flat. Okay. And in this case, you can also find that you can find a you can find a P a sub the projective sub bundle. Okay. Such that the restriction of F over P is surjective to the relative tangent bundle of P over T. Okay. So this is in fact our second example here. Our second example here. Okay. Our second example here. Here you just take a P to be the projectivization of P of E. Okay. You take P to be P of E here, and this gives you the second case. Okay, this is exactly this case here. Okay. Now you want to use this description to show that in fact you can descending this PD bundle to X. This is indeed the case because in the last step we show that X admits admits only one extreme contraction And you take this extreme construction from X to also maybe over T, and you take X0 here and T0 here. So this is a subset here. This is a subset here, okay? And you can show that this X over T is indeed equidimensional. And then it's a standard argument to show that X over T is in fact a projective boundary. Okay, so this is the ideal for our proof. So I think I stop here. Thank you very much.
So thank you, Liu Jie, for the nice talk. So do you have any questions? So I have one question. So, but
Yeah.
since I had lost internet connection, so I might ask some question that you already maybe you already talked about.
Yeah.
Can you come? So in your main theorem, is it possible to have PD bundle which are not Zariski locally trivial?
In fact, in my talk, it's possible because yeah, I can say that it's locally trivial in the analytic topology, but it's not necessary to be trivial in Zariski topology.
Mm-hmm. So do you have any explicit examples?
No, I don't have any explicit example, but because in my example, all the example in fact is construct. First of all, first you construct some vector bundle in fact. Okay, you use a representation theory to construct a vector bundle, and you take the projectivization of a vector bundle. Yes. Yeah, in this case, it's always trivial in the Zariski topology. But I don't know how to use the representation theory to construct an example. For example, you use a representation of the fundamental group in the projective linear group to construct a projective bundle. Mm-hmm. Okay, I don't know how to use such a construction, but principally it's possible. Yeah, from our proof it's possible because we care about we care only about its projectivization. We don't care about the vector bundle itself. Yeah, I mean this representation may be given directly by the projective representation. Maybe not come from a linear representation.
Mm-hmm. So every known examples, explicit examples are like direct factors of related tangent shape.
Yeah.
Mm-hmm. Thank you. So more questions? Maybe let's still wait for a few seconds.
Yeah. So there's some problem with my internet during my talk.
I think so far, yeah, so far so good.
Okay.
Okay, so if there's no more question, let's thank Liu Jie again.
So thank you very much. Thanks for your attention.
We'll resume at 30. So either 3:30, 4:30, or 5:30, depending on where you are at eAsia. So see you later.
See you.
See you.